Hello everyone, I hope you're doing well. I hope you're comfortably installed. Today we will continue congestion control in the internet and move on to BGP. We have seen that congestion control in the internet is implemented in TCP with several variants. TCP Reno, which is the historical and more or less standard version. TCP Cubic, which tries to improve a few things when the bandwidth is very large and the round trip time also is large. And we have seen that TCP reacts either to losses or to explicit congestion marks called ECM. We will see a few other details that will allow us to have now a complete view of how congestion control is done in the internet and in networks that use TCP-IP. So let's start with data center TCP. A data center is a large fraction of the internet which is very localized. It's a huge number of racks of PCs and switches, also routers, and it's used of course by the GAFAs, YouTube, Google, etc., but also by smaller size companies like Infomaniac, Switch Drive, etc. EPFL also has data centers, of course. What is special about data centers is first that they are in a private environment. So usually one company runs the data center and has full control and can therefore optimize everything inside the data center. Today, most traffic in data centers is TCP with very, very small latency, well below the millisecond. The bandwidth is huge, and the traffic volume is also large, with essentially two types of traffic. The external traffic, this is the traffic that between customers and the data center, and internal traffic, that's the back end. And if you look at things in detail, you realize that there is a combination of many short flows with low latency required. That's for the interactive users in particular, but also for internal computations that can be done in the back end. And you also have very large flows, which are, for example, backups and synchronization, which must run also very fast. So that's the context. Now, imagine you work at one of these companies. All your PCs are using Linux. In the lab, we will see that there are multiple versions of Linux that we can very easily choose. Which one would you choose for your data center? Today, for this poll, we will not use SpeakUp like we did, but we'll do an experiment with the polling feature of Zoom. So I'll ask Aladdin to start the poll for this question. Thank you, Aladdin. So we should see now you should see a panel where you can give your answers. Good, we will close the poll in a few seconds. Last opportunity to click. I close the poll, I end the polling, and you should see now the majority vote. The majority vote is saying D, so the red bar doesn't mean it's the correct answer, it simply means that's the majority vote. In fact, there is not a single correct answer. There are two correct answers, which would be B and D. Why is that? We do need ECM in a data center, because without ECM, that means that we will have the phenomenon that we've seen before of buffer bloat, which means that all the flows will saturate all the buffers before they're able to react to congestion. And since there are a large number of interactive flows, we do need to have ECM. So we would typically deploy ECN with Cubic if it works. In the lab, we are not always able to make ECN work with Cubic, so perhaps you would do it with Reno. But the performance is likely to be the same because the round trip time is extremely small here for Cubic and Reno. Still, so if you run a data center, you would like to run ECN. Data center TCP runs ECN, but with a modification that is motivated by this. Furthermore, we would like to optimize again for the problem that we've seen that motivated TCP cubic, which is the fact that there are large oscillations. So with TCP cubic, those oscillations are less large, and they move faster, but still these oscillations cause some inefficiency. The average rate that we get is not the max here. So we would like to have a smoother decrease here. When we have negative feedback, instead of simply doing this abrupt decrease, which is 50% if we use Reno, we would like to do something smoother. This is exactly what data center TCP is about. So data center TCP takes all the same elements of standard TCP. So if the standard is Reno, it's exactly the same as Reno. But the multiplicative decrease is replaced by a factor, beta, that depends on an estimate of the probability of dropping packets, of receiving ECN marks, which is a fraction of packets that are marked with congestion here. So if P is this, remember when we have ECN, in the standard operation of ECN, the ECN we use with Cubic or Reno, we mark the packet, the echo in the TCP header, and we keep marking them until the source declares that it has done a decrease. And the hope is to do one decrease of the window per round trip time. In data center TCP, we deviate from this. We do things differently. We constantly receive a stream of acknowledgements that are marked or not marked, and we count with a sliding window mechanism and an exponentially weighted moving average. We deduce from that an estimate of the probability of congestion P, which is, roughly speaking, the proportion of ACKs that we receive that are marked. And then whenever we have to do a decrease when this P is non-zero, when we receive over a window packets, at least one packet that is marked, we decrease by this quantity, which is 1 minus P over 2. So you see that if P would be 100%, which is what we have in standard ECN, we reduce by 50%. But if P is much smaller, of course, we reduce by a much smaller amount. So this will have the effect that as soon as a single packet is marked, we will have a small information that will tell us we'll have a very small value of P, and the source will decrease. So we will do a very small decrease, and in many cases that will be more efficient. Okay, DC TCP is deployed in many data centers. Linux, Windows have it. Now what happens if somebody has the idea to do both standard TCP, which is, for example, Cubic with ECN, and the other DC TCP? What would happen for the competition between those two flows? So here we will also start a poll. I will close the poll in a few seconds. And you will see that the majority answer says B, which is the correct answer. It is the correct answer because first, Cubic or Reno are probably the same in this setting. So we can compare to Reno, which is easier. Reno will decrease whenever there's a negative feedback by 0.5, whereas DC-TCP will decrease by 1 minus P over 2. And the rest is the same. Therefore, if we're in the operation mode where cubic is the same as Reno, therefore, the decrease is much less with DC-TCP. So a DC-TCP connection increases in the same way when everything is okay, when it receives only positive feedback, but it decreases less when it receives negative feedback compared to another TCP connection that would be using Reno or cubic here. Therefore, the one that decreases more will of course back off more and will take a larger time to get back to a higher rate. So it will receive less throughput. That's a superficial analysis, but that's the idea. We can do more experiments to see that, and we will see it very easily. In the lab, we will be able to experiment with DC-TCP and TCP cubic. You will see that kind of things. So, but this is a problem. DC-TCP is a good solution if you are running an entity, data center, for example, where all flows are running DC-TCP. But even in your data, which is probably true for all your internal flows, because you control, hopefully, the software that runs on your servers. But you may have also other TCP connections that come from the outside. And those TCP connections, you may not control which version of TCP is used because it's customer or outside entities that use it here. So if you use DC-TCP, you cannot simply deploy it together with other TCP versions. It must be separated here. So that's one of the consequences of this scheme. And this is what happens today. So if you run a data center, you will run the flows, the internal flows, separately from the flows that interact with the outside using something that is called class-based queuing. What is class-based queuing? Well, it's a way to modify the competition between flows. So far, in everything we've said, all flows are treated the same because the congestion control is end-to-end. It's only the source that reacts to feedback it receives from the destination and accumulated over the path. So in routers, all flows are the same. But of course, we can modify this by having separate queues for separate classes of traffic. So this is used by having routers classify packets using various ways, like we've seen in SDN. You can use what is called access list to decide what you do with a packet based on something. And what is that thing? Well, it can be, for example, the addresses. If you are in a data center and you want to separate between the internal flow and the external flow, you will look, for example, at the source and destination IP addresses. If both are inside your data center, it's an internal flow, and you put it into the class of internal flows. Then, within routers, we can put a queue for every class, and every queue will have a guaranteed rate. This is implemented, for example, very typically with deficit round robin. Deficit round robin is very similar to weighted round robin. Weighted round robin is something very simple. Weighted round robin is a scheduling policy that is used practically everywhere in servers. If you have two classes, for example, and you would like to give 20% of the capacity to the first class and 80% to the second class, you will give a weight of 1 to the first class and 4 to the second class, and you will serve the queues in rounds by saying, in the first step of a round, I serve 1 packet of the first class. In the second step of the round, I will serve 4 packets of the second class. This is weighted round robin. Round robin without weights means at every round you serve exactly 1 packet of every class. But by giving weight, we can guarantee a certain rate that may be different for different classes. Weighted round robin is more for real-time systems or for schedulers done in processors. When we talk of packets, the equivalent is deficit round robin, which is the same, but takes into account the fact that packets are not all the same size. So it is used in data centers when we have DC-TCP, for example, to separate the internal from internal flows. It is used also in networks where we have non-congestion control flows. For example, real-time flows in industrial networks. We'll see an example in a second. It's also used in enterprise network, where you may want to separate not just the internal flows using DC TCP, but perhaps all the internal traffic or the traffic that you use for a certain type of applications. For example, AT&T does that for providing excellent quality to video conferencing. All the video conferencing traffic of AT&T is in a special class where it will receive more bandwidth than the rest of the traffic, like when people access the web. Here's an example in an industrial network setting that, in fact, very similar to a network we have at TPFL. So we have sensors, here in that case PMUs, they sense the electrical grid, and they stream data to a control center, which is, for example, S1 here. Now, those sensors, they are made to generate data at a given fixed rate. Here it's a sensor that sends, for example, a large numbers of electrical sensing devices and the aggregate flow, and it does one measurement every 20 milliseconds, and the aggregate flow is, for example, 1 megabit per second. Those are typically non-adaptive application. That's an application that must work at this rate. If the rate is below, the application will fail. It will not, the control center will not receive all the measurements. And if you give more capacity to this, it's useless. So it cannot adapt. Non-adaptive applications are frequent in industrial settings. If you have non-adaptive applications, we have seen that there are lots of problems that can occur. We can have congestion collapse. We can have inefficiencies. So if you have non-adaptive applications, you should separate them from the rest of the network, which we do here by putting them in a class which is called class 1. And then you should not only separate them, but you should also do what we call traffic engineering. You should calculate the rate that you allocate all over the paths of those applications such that the rate is sufficient to serve them. So here we have one application that on this link, we have one source on this link at 1 megabit per second. Here we have two, so we need at least 2 megabit per second. And here the allocation is conservative. We say we allocate 2.5 megabit per second to the red class. Since there are only two machines that stream at those bit rates, that will be sufficient. So there will not be congestion collapse because the rates are fixed and the link rates that have been calculated are above the capacity. So we are never getting into the scenarios we've saw before where we start having congestion collapse because of cascades of drops. Here, I assume that in this network, the rest of the network, the rest of the traffic, the best effort traffic, which is typically congestion control, will use the rest. So here I have a second class, and on this simplistic example, the links are 10 megabit per second, and class 2 has 7.5 megabit per second. When we do such a scheduling mechanism, for example, we could do that with deficit round robin by having a weight which is 3 times larger for, or a quantum which is 3 times larger for the blue than for the red, but it will have an effect that is called borrowing. This effect is that with such schedulers, I said with weighted round robin, I serve 4 packets of the second class in one row, but I will serve 4 packets only if there are 4 packets to serve. So if the one of the classes is using less capacity than what it is guaranteed, the delta, the difference, can be claimed by other classes, which is typically what would happen here. Here the blue traffic is congestion control. It's adaptive. It will exploit as much of the capacity as it can. So it will be able to borrow the capacity that's left over. For example, on this bottleneck link here, there's only 2 megabits of red traffic that is flowing. So this blue traffic will see 8 megabit per second available here. This is called borrowing, and this is how typically class-based queuing is implemented. So if we go into more details of this example, this toy example, I have two TCP connections. The red flows, they will get exactly 1 megabit per second, assuming I'm streaming a large amount of data, but over TCP, so adaptive application. For example, I'm transferring files here. at which rate will I be able to transfer the files? How much capacity will be allocated to those two blue connections? We start a poll. Okay, we close the poll. In parallel, I answered some questions on the chat. I end the poll. And the majority says B, which is the correct answer. As we can see here, since the red traffic is not adaptive, it will send constantly at 1 megabit per second, which means that on the first link for the blue traffic, there are 9 megabits per second available, on the second link 8, and on the third link 8. So for the blue traffic, it is as if we had only this network with reduced link capacity here. Now, how do we get the rates? Well, here it's fairly easy. One solution consists in saying TCP allocates the rates as if it would be solving an optimization problem where it maximizes the total utility, where you use the utility function of TCP. The function is the same because the RTTs are the same here. So since the function is the same, it will maximize u of x1 plus u of x2, subject to the constraints. The constraints are given by the 3 links here, but they boil down to only this constraints, x1 plus x2 less than or equal to 8. Since the utility function is the same, probably it's obvious that the optimal is symmetric. It should be 4 megabit per second. So that's one way to have the answer. We can also do a bit more heuristic by say if I do the max min fair allocation or the proportionally fair allocation, I can compute both and they're equal. Since TCP is in between, probably it will give this here. Voilà, so this is how class-based queuing is deployed. Of course, there was a question about in the internet, can we deploy class-based queuing? I mentioned that AT&T might be doing it for video traffic, but it is for the AT&T video traffic, not for the external traffic. So operators like AT&T offer private services to big customers, for example, who want to run video conferencing over as an AT&T application, not as an external application that runs over the network. There is de facto what is called net neutrality, which is implemented or is not implemented, depending on the countries. Net neutrality means that, in fact, you cannot do class-based queuing in the internet for the public traffic. There are other reasons for not being able to do it. It is that the absence of a payment mechanism. Of course, if there would be a different class of traffic for voice and video than for other traffic, and if this class of traffic receives a better treatment, then everybody would use it. So it's if there is first class and second class at the same price, then everybody will go into first class. So this is another reason for this not being deployed at least not in the general public internet, but it is deployed for the applications that internet service providers may offer. It is also deployed in cellular networks, where cellular networks are allowed to offer differentiated service depending on how much you pay for the access. Voilà, we've talked of TCP applications, but of course, there are also UDP applications that should do congestion control. We've seen some that cannot, the streaming application at a constant rate, but there are other applications that can and should. For example, QUIC. QUIC is a framework more than an application that replaces TCP in the Google ecosystem for much of it and uses UDP. So of course, such an application that use QUIC should do congestion control. Here it's fairly easy because QUIC is very close to TCP. It has the concept of sliding window and packet acknowledgements. So it's very easy to imitate exactly what TCP does, which is what QUIC does. QUIC uses exactly the same congestion control module as TCP does. So it is de facto doing the same as TCP. But there are other applications that may send large volumes of traffic that use UDP. This is typical of some real-time interactive video applications that want very short delay. And then when you do a video application, instead of uh, instead of control, so I see that there's a question on the chat, how is UDP with acknowledgements different than TCP? Of course, UDP does not have acknowledgements, so we'll talk about QUIC a bit later. QUIC creates a QUIC header on top of the UDP header, and inside the QUIC header, there is a sequence number and an acknowledgement. So it's doing something like TCP on top of UDP. Of course, it's not UDP that provides the acknowledgement. But there are other applications, typically those that use video and audio, where there is a real-time constraint. When we are talking over the internet, not like me today, we're not using that type of application in Zoom as far as I know, but this is also not very strictly real-time. You can perceive that there is a delay of several seconds in a Zoom conference, for example. If you want more aggressive and higher performance applications, you would like much larger delay, less than 200 milliseconds. If you do this, then you cannot simply do like TCP does, send an acknowledgement, repeat when there is a loss, etc. So those applications, they do not correct losses by repetition. Such video applications, they correct the losses by video and audio specific mechanisms. For example, an audio application typically sends one sample of audio every few milliseconds. If one sample is lost, when the receiver will not ask the source to resend it, it will try to mask the error. For example, by repeating the previous sample, or by doing an interpolation of if there's a gap, if it has out of 3 samples, the second one is missing, it might do an interpolation between the first and the third. So there's a large number of tricks that are used by audio and video to mask errors. And perceptually, this is much better than repeating, which would cause a large delay. In addition, such applications can change their rate by changing the coding scheme. For video, you can change simply the resolution of the image. For audio, you can also change the sampling, the number of bits that is used by the samples, and so the sampling depth, and also the frequency at which you sample. So you all know MP3 that can run at very low bit rate, 64 kilobit per second, or you can use FLAC instead to run at hundreds of kilobits or 1 megabit per second for one audio flow. So you can modify this, and this is what these video conferencing applications do. So such applications, they don't have a window like TCP or QUIC has with acknowledgements and all that stuff. Instead, they have a module that can control the rate by changing the coding parameters. Such application should also react to congestion. And the dogma in the internet is that they should do it by imitating exactly TCP. I call it a dogma because it's based on the feeling that TCP is the best thing that humanity has invented in the concept of congestion control. Therefore, we should imitate it. and this is called TCP friendly. So there is, for example, a standard protocol, TFRC, the TCP friendly rate control protocol, that says the following: such an application that can adapt its rate must still receive feedback from the destination. But the feedback is not in the form of acknowledgements with the intention that if a packet is lost, we will retransmit it. No, the feedback is simply a statistic every 100 milliseconds, for example, how many packets were lost or marked if you have smarter things. But typically, here we have only losses. And then you send, using the RTCP, so real-time control protocol, you send that information back to the source, who can then estimate a loss probability with a bit of filtering, probably. So the source has an estimate of the loss probability, and then it will set the rate to this formula, which you recognize here is the TCP-Reno loss throughput formula, which means that, at least roughly speaking, this source will send at a rate which is the same that the TCP-Reno connection would have with the same loss probability. Therefore, it will also do all the good things of TCP-Reno. In particular, the system will be Pareto efficient, and we will not have a congestion collapse, and we will have the fairness that TCP-Reno has. Roughly speaking, of course, because this formula is only approximate, and there are also sampling biases. You don't measure things in exactly the same way as TCP does, so there are biases, but roughly speaking, it provides the same, and this is the what should be done in the internet if you have a UDP application that cannot imitate TCP, but must adapt. Voila. This is all the elements of TCP, of congestion control. I summarize them here. Congestion control in the internet, like in any network, is mandatory. Otherwise, we will have traffic problems, congestion collapse, and inefficiency. And it is implemented in the transport layer, in TCP, or in the application layer, in fact, in TCP or in a TCP-friendly UDP application. When it's done by TCP, it's done by controlling the window with additive increase, modified by a cubic increase once the additive increase has reached a certain level, if we use cubic, and multiplicative decrease when there is a loss. By default, TCP uses loss as congestion signal. It can also use ECN, explicit congestion notification, as a supplementary congestion signal, and this has the benefit of avoiding to fill the buffers, which has drawbacks in terms of latency here. And orthogonal to all this, we do class-based queuing to separate classes of flows, either because they don't react to congestion or because they use different reaction congestion mechanisms. Voila, that was the end of our module on congestion control. Without any further transition, we dive now into another topic, BGP, external routing. BGP, as this image is illustrated, is self-organizing. BGP is at the heart of how the internet performance is. So BGP is the protocol that is run between internet service providers. So we will see it in two phases. We will see what it does and how it works. I'll try to separate the two, as I try always to do in this course here. So self-organization in the internet means that the internet is heterogeneous. There is not one entity that runs it. And even if there would be one, it would be too large. So the internet, like what is called the international community, is not run by the entity. Even there is United Nations, but they don't really run things. It runs by the collect emerging behavior of all the independent actors. So, but we still need routing. The problem that caused us to talk about OSPF still exists in the internet. How does a router in Switzerland know in which direction send a packet with a given destination address? That might be in China or in the US. So we still need to run a routing protocol, and this is done by having a hierarchy. We have the internet is split into autonomous systems, and inside autonomous systems, we have things like OSPF, which are called interior routing protocol. And between autonomous systems, we have BGP. Inside a domain autonomous system means the same. You can use whatever routing protocol you want. OSPF is the most widespread one, but there are many, many other ones. Proprietary one like EIGRP, old ones that are very simple and are still used when you have very small toy networks like RIP that we'll see towards the end of the course, and other ones that are used for special purpose, for example, in data centers. Between domains, in contrast, you have no choice. You must run BGP. There's only one protocol, and it's the BGP4, the version 4 of BGP. A bit of terminology. A domain is called an AS, autonomous system, or also an autonomous routing domain, ARD. There's a subtle difference that most of the time I will not consider because most technical literature doesn't, but in the standard there's this difference. The main difference is that every AS, every domain, has a number, or every AS that has a number, every domain that has a number is called an AS, and a domain that does not have a number is called ARD. In principle, every domain should have a number. This number was originally 16 bits, but it has now been extended to 32 bits. So an AS number is 32-bit, and it's written in dotted decimal notation. It's a strange place where we see again the dotted decimal notation showing up. It's 2 blocks of 16 bits, and every block is denoted as an integer in base 10. There are also private AS numbers. Those are those numbers here, where the first 16-bit word is 0 and the leading one are above 64,512. For example, Switch, which is the provider of all universities in Switzerland, has AS number 559. Open Transit, which is a international transit operator, has this number here. EPFL, which is also a domain, does not have a number, but it doesn't have a number because EPFL accesses the rest of the internet via Switch. So in order to simplify the BGP table, we try to not give numbers if not necessary. So for the rest of the world, EPFL is seen as a part of Switch, therefore does not have an AS number. So we have two types of protocols, BGP and interior protocol. How do they interact? Well, this is showing here. Remember that with OSPF, you can have areas here. So you can have a large domain that will have areas, but for BGP, this is treated as one single domain. BGP ignores whether there are areas or not. And BGP typically runs between routers that are at the boundary of the domains. Unlike OSPF, where OSPF we saw that D4 is a router area, is a border area router. It is in both areas. It's in backbone area and in area 1. In contrast, typically, maybe a bit different sometimes, but in principle, there is one BGP router at every side of a boundary. And this is because typically BGP is used between domains that have nothing in common. So it's easier to have a router each and agree simply on a link rather than having a router that would be shared by the two. And as I'm showing here, you can have whatever routing protocol you want in your domain. That doesn't play a role, but between routers, between domains, you must use BGP and the current version, which is version 4. BGP handles both IPv4 and IPv6, and it is used to compute paths from one router in one domain to any network prefix anywhere in the world here, using the method of path vector. And another important aspect that we will see that was not present in OSPF is policy. So BGP is based on path vector routing. BGP is not like OSPF, is not computing shortest path. The reason for that is that since it is for the heterogeneous world, it is too much to ask that everybody would agree on cost. If we would use the shortest path routing, we would need to agree what is the cost of the link between domains, and those costs would need to make sense globally. Perhaps a Chinese cost is always between 100 and 1,000, whereas a Swiss cost is always between 1 and 10. So globally, then this would not make sense. We would need to normalize the costs everywhere, and nobody is able to do that. The world is not so well organized that we can do this. So we don't use shortest path routing. Instead, we use path vector routing, which is illustrated here. Path vector means that a route between a route in the internet collects all the elements of the path here. Let me illustrate here. Here I have a first domain, A, that has two prefixes, N1, N2. And the goal of BGP is that domains like E know how to go to N1, for example, here. So via BGP, A will inform B that it has those two prefixes, N1 and 2, and then B will inform E that it has received it. But what B will do, it will concatenate the path of ASs. So B will say to E, I have a route to N1 and also to N2, and the path that I give to you is AB or BA, depending on how we write it here. So E, therefore, will know from B that it can reach N1, and the way to reach N1 is going via a path, which is B, then A. Similarly, C and D will do the same thing, and domain E will learn from D that there is a path to N1, which is via domains D, C, A. So that's the very principle of BGP. BGP accumulates the path in contrast to systems like OSPF, where OSPF will care only about the distance to a destination. Here, E knows not the distance to N1, so it has two choices. It can go via the top link or the bottom link, but here we don't care about the distance, but the path. So E knows in order to go there, I have to go via B, and here, in order to go to that destination, I have to go via D and C. Then E can take a choice, which is much easier to take because now I have the complete description of the path. For example, a very common rule is you take the shortest path counted in number of domains. This is based on the hypothesis that if you go via two domains, the performance is probably less good than if you go via one. This is perhaps what E did. Each preferred this path because it is shorter in number of domains, which is called the AS path here. But every possible other decision is possible. For example, E might say, I don't like C, because C is a domain that is not cooperative with me. It does perhaps some non-network neutrality. Perhaps the traffic that comes from E is given very low priority in C and gets very bad treatment, or even some destinations are killed because this is a country that does not allow any traffic to go through it. So E might decide based on completely out-of-band mechanisms that he doesn't like this because by looking at the path, it says C and E does not like C. Or B, for example. So by having the complete path, it is possible for a domain to decide using what we will see is called policy. So that's the first part. And in what I have shown so far, there is only external BGP. BGP is used only between routers at the boundary. But here, if I have four routers, C, D, E, F, in the domain that's in the center, those four routers, they will talk to the outside, but this information must also be spread into the network. And for two reasons. First, for allowing the internal network of the domain D3 to get all the information, and also to participate in global BGP to pass the information. For example, C receives information from A, and it needs to forward it to E so that E sends it to G. So we need also an internal mechanism to disseminate the information that is learned via the boundaries, via the external peering. This protocol is also exactly BGP. It could have been something else. We could have used a database mechanism. We could have used whatever system. But this is not what is done in the internet. It is BGP. So inside network D3, there will be also BGP exchange of information, not just between A and C, but also between C and D, for example. In fact, by default, we'll see that we can deviate from that. By default, inside one domain, all BGP routers must be connected with each other by TCP connections. So here I have 4 BGP routers, C, D, E, F. They are connected by what are the plain lines here, which are TCP connections here. And they exchange all the information. And the beauty of it is that this is the same protocol as on an external boundary, with only 2 rules that are different. The first rule is that routes, so information that is learned internally, is not repeated internally. So, for example, B will learn something, D will learn something from the outside. It will repeat it to all routers internally, C, E, and F. But if it has learned something from C, it will not repeat it internally, because the assumption is that C has a TCP connection with all other BGP routers. So it's the job of C to repeat it, not the job of D. So we see it's very different from the way OSPF is working. So this is the major rules. iBGP does not repeat iBGP information. And another obvious rule is that since we are inside the domain, we don't accumulate in the path the AS number, which we do only when we cross a domain boundary. Voila, we will do a break and resume at 1:15.